Maybe?
Yep.
Okay, good.
If you have brought your laptops, you can download the content that we're going to be using at github.com/parkergarrison/overflow. We're going to be going through this live. All right, it's 4 o'clock, so let's get started. As I said, you can download the content here with a git clone, https github.com/parkergarrison/overflow. And to ask questions, we're going to be using Slido, so you can go to slido.com/overflow, and I'll address the questions as we can get to them. When many people try to learn a complex topic, like how to exploit buffer overflows, they may get too into the details first without understanding how it works overall. For example, if you were trying to learn how to draw an owl, you might want to first draw 2 circles to get the base of the owl, and then the next step is clearly to just draw the rest of the damn owl, right? With this, you can't alter the owl in any meaningful way if all you're looking at is the line segments there. So instead of taking a reductionist view, we're going to first do an overview of memory in the stack for about the first third of our presentation, and then get into the details with exploit mitigations and bypasses for some common exploit mitigation techniques. We're going to start with memory layout, then talk about stack frames, and then how a buffer overflow can be used to take control over a program under what conditions it works. As I said, if you have burning questions, please ask them towards the beginning of the presentation, as this will make it easier to understand the rest of the presentation and probably help out other people who didn't want to ask the questions or even just didn't even think that they had those questions at first. Virtual memory is composed of multiple segments. Today, we're going to be only concerned with virtual memory, as we are when we're writing a program itself. The virtual memory is paged to physical memory, whose addresses are different than these. But the program acts as if it has access to the full memory, which for a 32-bit program is 4 gigabytes, and for a 64-bit program can be much more. Each of these segments has a different functionality. I've included the segment mem.c program in the directory so that we can go through it and see what each of these segments are used for. So if you've done the git clone, you should have this stuff here. I'm going to remove this and reclone it. and change into the overflow directory. And let's compile our segmentmem.c file. You'll find the instructions in the README file. We can do a less on readme.md, and alternatively, we can just copy it from here. This will be useful for repeating some of the commands once we get down to them. And let's run the compiled program. So we see all of these addresses here. Let's try to make sense of what exactly they are. We have the address in the .tet segment. Let's see what that's referring to in the original program. We're in the segmentmem.c. So this address in the .tet segment is the address of the main function. So code in the program is stored in the .tet segment. Then next up on the stack, we have the .data segment. This contains initialized data. Our example here is the static string hello, which is compiled into the program, and also an integer which starts out with a static value and is inaccessible to the whole program. There's also the .ro data segment for read-only data. Next up is the BSS. This historically stood for block started by simple, but now it's just used to store uninitialized data, such as this integer that hasn't been initialized. Then there's the heap. The heap is used to store dynamically allocated memory. For example, that's what's allocated with malloc. We don't know how much memory we need to allocate in the beginning, so we can't put it at a static place in the program. It's allocated when the program is run. There's also shared memory. And the one that we're most interested in here is the stack. The stack is different from all these other segments because there's a different stack frame for each function. And we'll get into that on the next slide. But an example of a stack address here is bf82ddae. The stack grows down towards lower memory addresses, where the heap grows up towards higher memory addresses. When we say that the stack grows, that means that the address of the stack pointer is decreasing. So that's something important to note for when we do our exploits later. Stacks and function calls. The caller and the callee are both responsible for some of the parts of setting up and tearing down for a function. In different calling conventions, they're responsible for different things. For example, cdecl and fastcall. But over all these conventions, there's some similarities. Let's take a look. First, we'll review some assembly language instructions. When we push a register, and this may be new syntax to a lot of you, so ask on Slido if you have any questions. I see there is one in so far. When you push a register, that moves it to the current location on the stack, and then grows the stack by subtracting it by 4 in a 32-bit program. When we pop from the stack, we get the value pointed to by the current stack pointer and add to the stack pointer to shrink the stack. When we call a function, we push the current instruction pointer to the stack so that we can get back to the place we were before the function started executing, and then jump to the start of that function that we want to execute. These three registers that we'll be most concerned with today are EIP, the instruction pointer, ESP, the stack pointer, and EBP, the base pointer. So let's get to the caller. The caller has to load the function arguments to the stack, which it will do by pushing them appropriately. And then it just simply call function name. We can see back here that it's going to push the current execution location of the stack and jump to the start of our function. So let's look at an animation that I made. So at the very beginning, ESP points to the top of the stack is always points to this top of where we've been pushing our variables. When we call funcName after pushing our arguments, the EIP value is saved to the stack, and we jump to the beginning of the function. EIP is not shown on this diagram. This diagram shows the stack segment, which if you remember from here before, the stack segment has higher values and grows down. The stack and tet segment should never overlap. A pointer that's EIP is supposed to point to the tet segment always, and never point to the stack. If you go to the offsprings talk later tonight, you'll learn you got to keep them separated. So now we're in the callee. This is its own separate function. It has to save the location of the parent's base pointer so that the previous function can address its variables properly and close properly as well. So it pushes that to the stack. ESP, of course, decreases. This is an upside down diagram. And then we need to make room for the variables in the current stack. We set EBP to the base of the current stack and then subtract to make room for it. So at the end of the function, we set ESP equal to the value of EBP. If I didn't make it clear before, the move instruction is like a higher level language as equal instruction. This is setting the value of ESP equal to the value of EBP. If we used another assembly language notation, such as AT&T syntax, stuff is reversed and it's a bit harder to understand. But remember, this move instruction means that we're moving into the value on the left. We've already covered the push and pop here. So then we pop into EBP. ESP is pointing right at EBP, so that means that the correct save frame pointer value is going to go into EBP. And then we return, so we pop this value, which is the saved instruction pointer, into EIP. And now the EIP is pointing at the proper place, and ESP is pointing back to the rest of the function. Depending on the calling convention, the caller may need to shrink the stack to get rid of the arguments that were patched to the new function and continue execution. Okay, so I'll stop. Were there any questions from this section? Someone asked, I was told that even though ASLR and DEP help, it doesn't actually prevent overflows. Can you elaborate? Yes. So let's look at what might happen now if we have a buffer overflow. Let's say that the amount of data that is entered into the variables here is not monitored. One of these variables is read in from standard input, and the size of it is not monitored. So, what useful things could we overwrite that would make us have control of the program? So let's go through it again for the function epilogue. We set the stack pointer equal to the base pointer, okay. We pop into the base pointer and return. This is the part where we're going to want to take control of the program. And I will put out a poll here, if you're on Slido. Which register contains a value that we might want to jump to? So we're not overwriting the registers directly, but which register contains a value which might be useful to us? Would we prefer to control the value at the saved base pointer, or would we prefer to control the value at the saved instruction return pointer? All right, here's some of both. I'm getting some answers. Yep, and most of the answers, in fact, all the answers that have been in here so far are correct. We want to control the saved return pointer. If we overwrite this saved value, of course, we're not changing the actual register, but this value is put verbatim into the register when our function exits. So one of the catches is that we need the function to finish exiting normally. If we overwrite some critical data in the function that causes it to crash entirely, then we'll never get the value of the saved instruction pointer back into our function. All right, so now we'll look at how a buffer overflow might work. Let's look over here at the right. So the same thing happening when we start out with our function. We push the EIP to the stack and jump to the function name. We're going to push EBP, move the base pointer, set the base pointer equal to our new stack pointer for the new function, make room for the variables. Then when we write whatever we want here, and here we're overwriting the save return pointer with just the character uppercase A, which has ASCII value 41. So that's 4 times we have 41 in here. So we set ESP back to the bottom here. We pop into EBP, so now EBP has this value that doesn't point to anything meaningful because we overwrote it with the A's up there. Then we return to the location AAA as well. So that will get us to a location that probably doesn't contain any useful data, and we'll get a segmentation fault because we're trying to access a virtual memory address that has no correspondence to a physical memory address. All right, let's look. Are there any other questions so far? So I'll answer that question now about even though ASLR and DEP help, they don't actually prevent overflows. Yes, now you should see that that is correct, that they do not prevent overflows because we were able to overwrite the saved return pointer regardless of whatever functionality is enabled. We're just reading in more data than we should. So now let's get down to the nitty-gritty. We're going to start out with exploiting a program that has no mitigations enabled. Here's what we're going to be using for our exercises. There are 2 separate files here. We're going to be using a separate file for exercise 2. I haven't merged them yet completely. So here's our first exercise with no mitigations. Be sure you're in the repository that was cloned. And we're going to look at our README file to see how to compile our exercise 0. So we're going to compile our file without the no execute bit. We're going to be using these compiler flags. And quitting Vim is not covered in this presentation. So if you get stuck in Vim, I recommend just hitting the X button and opening a new terminal. So we're going to do GCC, wisdom.c, tag G, tag F no stack protector, in case canaries is the default, which is usually not. We'll get to canaries last if there is time. And tag Z exec stack, returning off the no execute bit, NX, or DEP as it's called on Windows. And we're going to output to wisdom e0.out. And you'll see we get all these warnings here. Warning, get sys deprecated, all this stuff like that. So that just shows poor programming techniques. We should indeed have the actual file that was compiled, though. We shouldn't have any actual errors. We should just have warnings. So if we run our file, wisdom.e0.out, we will see what this program does. All right, so we can log in, log out, view the status, receive wisdom, and add wisdom. Let's try looking at each of these functionalities. We'll log in first. Okay, reading 33 bytes for the input. This might be interesting. Let's put ABC as the user ID. Okay, we're logged in. Let's try to log in again while we're already logged in. Oh no, double free or corruption. Looks like this person didn't know what they were doing when they wrote the program. But it also looks like the operating system is protecting us from a potential double free error. So let's continue looking for other possible vulnerabilities with a manual fuzzing technique. There are more advanced fuzzing techniques you can use. For example, Sully is a Python framework that will fuzz a program for you if you tell it what fields are in the program. For example, you might want to use it to fuzz a complicated protocol like HTTP to see that Wireshark can process the fields correctly and doesn't have a buffer overflow. But for now, this program is simple enough. We'll just look through it manually. All right, so we'll log in, and then we'll log out. Seems like there's a problem with the logout. We'll log in and then view status. Okay, that just tells us our user ID, which seems it's the same random thing regardless of what we put. Let's receive wisdom. That might be interesting. Don't drink coffee past 4 p.m. unless you want to stay awake until the a.m. That's good. A great shell to use is bin bash. And if you're under pressure, then stop, collaborate, and listen. And we can add our own wisdom to it. Enter a title. We'll do title. Enter some wisdom. Put some wisdom there. Let's see what happened. We can receive the wisdom again. And we see that it got added to the list. We don't know what happened to the title, if it's even actually doing anything with that at all. See what the status of our program is. Still the same user ID, so that didn't change. All right, now let's see what happens if we put in more data for the wisdom, as we talked about here with writing in so many A's as to overwrite the save return pointer. So I've included a script in the GitHub repository as well. And it's called patgen.py. You'll give it a start and optionally and also an ending index. So let's generate 300 characters and see how the program handles that. There's a similar tool available in the Metasploit framework called pattern create and pattern offset. Those took a long time to run on basically all the systems I was using them on. They took about 10 seconds for no apparent reason, so I decided to write my own. We'll enter this into the title field and enter something else in the wisdom field. We could put in the next 300 bytes the pattern. Segmentation fault. So it looks like we overwrote something. We probably overwrote the save return pointer. And to see exactly what we've overwritten it with, we're going to use GDB to analyze the program. So in our example that we're doing today, wisdom.c would be a program that we know is being used on a system that we're penetration testing. And we have access to a binary of the program, but potentially not the source code. So we're going to exploit the code by only using the binary. But since we have the binary, we can attach a debugger to it. We're going to use GDB, the GNU debugger, and also you'll see in the README file, we're going to be using the PETA extension to GDB. So if we do a less on our README file, you'll see at the very top how we can clone the PETA repository and add it to our GDB initialization file. If you've already done it, you'll get that. So let's go with GDB. We're going to run that wisdom file again and pass it the process ID of the wisdom.out file, pgrep wisdom. So now if you try to use this program, say we do the add wisdom again, and then the program hangs, you can see that it is being debugged. So let's continue. The program will continue again. We'll enter the same stuff in both fields. We entered what I had copied there into the title. Let's enter the second thing. We'll enter it into both of the fields, see what happens. Now stopped reason, sig-save, that's segmentation fault. It's trying to access this memory, sits-A, sits-5, sits-141. Can anyone tell me what that is in ASCII off the top of their head? Well, you don't have to, because we have the pattern index program. Wouldn't be surprised if someone in here could, though. So it will tell us, depending on if we're a big endian or little endian system, how far this offset is into the pattern. And remember, this pattern started at 300. And we're on a little endian system, as you can see. an x86 system. But what's the difference between these, and why would it be a different value if we're on a big endian or in a little endian system? So the terms big endian and little endian actually come from the book Gulliver's Travels. Big endian, breaking the egg by the big end, was the way that people always broke their eggs. But the king ordered people to break their eggs from the little end. Both ways work, but you can't do both at the same time. Big endian is the way that we represent everyday numbers. In decimal, for example, if we had the number 9001, we would represent it by writing the digits 9001. However, modern processors typically represent as little endian, unless we're on a different architecture, such as Spark instead of x86. So if we were using little endian and decimal, we would write 1009 to represent the same number, 9001. These are the same numbers, but they're represented in a different way. So we know we're on a little endian system. Our start end of the pattern was 300. So at an offset of 152 is where this value appears. So if we were to replace that with something else after 152 characters, then we would have control of the instruction pointer. So now let's see if there's anything interesting in the code that we might want to jump to. I'm going to run info functions in GDB. We see we've got lots of functions here. And I'm going to go through it from the top down and shout it out as soon as you think you've got something interesting that might be a function we want to jump to in order to get a shell. So we've got init, set buff, lots of interesting named functions. Which one of these might get us a shell? Yeah, what is this doing here? Shell? If we look back at the actual program source code, which we're not going to use to our advantage in this case, we'll see the shell function, debug use only, delete this before production use. Update, never mind, I deleted the last option, so there was no way that this could be called, right? Let's see if there is. So remember, we're on a little endian system, so we're going to need to put this address in what we might think of as a backwards order. When I was doing this talk for practice, someone said that they had me up to the point where I started putting the addresses in backwards. So it's important to note that we're not actually putting them in backwards for the computer, but the way that they're stored into memory when we're doing a raw write is writing from big endian to little endian, essentially. So let's write this address in reverse order. There would be \x4c, \x86, \x04, \x08. To escape it, we're going to use Python to print this out. 152 A's first. And then that literally, so that it doesn't get messed up as it gets printed out. That looks like what we want. I've included this program runescape.sh, runescape.sh, that will run the program escaped. So let's attach to our debugger once again. Quit out of this old instance of the program. And add wisdom after we join with GDB. Running the same command to get the process ID of wisdom and join to it. Let's see if we are hooked. It seems like we are. Continue. Enter a title. But we're not exactly sure which of these was vulnerable to the buffer overflow. We know it was one of them. Let's just put it in the wisdom field. Process 7501 is executing new program, bin dash. What happened here? Did we actually get a shell out of this program? I think we did. Now let's let's see if we can leave a message for the owner of this system. All right, and exit out of our program as our proof of concept to see if that stuff is actually still there. Yeah. So do your shell dance, and now it's time to move on to our next exercise here. If you were following along and got that to work, then great job. You learned binary exploitation a lot faster than I did. So now let's say that this shell function is not actually compiled into the program anymore. What might be a way that we could execute the shell code that was present in the shell function if we have to put it in the program ourselves? So I'll go back to the diagram here where we listed each of the parts of the stack when we did a buffer overflow. So once the buffer overflow finishes, we write whatever we want here in the data contents, even going down into what used to belong to the next function. We're not going to need it because we have no intent of returning to the next function since we're overriding the return pointer. Then this is where our registers sit. So what might be a useful register that we can jump to at this point to execute code on the stack? Remember, although the data segment and the stack segment should have distinct registers, without the NX protection, which is how we're going to still do this exercise with the same compiled binary, it's possible to get the value to move. It's possible to get the instruction pointer to go somewhere in the stack segment or any of the other segments, not just the data segment. So what might be an attractive register that we would like to jump to? So we've got this situation here. EBP is not pointing anywhere meaningful. We got ESP pointing to where the old arguments of the new function were. So we want to know what to put in EIP so that we can take control of the new function. And if anyone wants to shout it out, they can, or I will put up a poll again. Yeah, we want to jump to ESP because that's a safe bet where we can jump to. If we try to jump to the very beginning of this thing, how exactly would we do that? We'd have to get ESP minus 156. So let's just jump straight to ESP. So let's compile our new program. Go back to the readme.md file. And we're going to compile it essentially the same way. So now we've got our Wisdom E1 compiled up there. And we're going to want to go to do this register. So let's run our program again and see what address we might want to put into the save return pointer instead of the system address. I mean, instead of the shell address. So quit out of this. And run our wisdom e1.out. We'll escape it again. Escaping our user input. And now we're connected to the program as a debugger. And let's see if we can get the value of the stack pointer as this function is finishing up. So let's go back to our README file and copy the G2B command that we're going to be using from there. We're going to generate the same pattern first to put into our program. And continue in our debugger. Paste that in there. So we do get the segmentation fault indeed. And let's see, after this happened, where the stack pointer is pointing. So this is the value of the stack pointer. And make sure that you have ASLR off before running this. I forgot to turn it off on my system. We're going to exploit the program with ASLR on, though, a bit later. Looks like the projector got disconnected. All right, and we're back live now. So we're going to use the instruction from the file to turn off ASLR, echo 0 space to overwrite procsys kernel randomize underscore VA underscore space. And run this program again. I didn't type in number 5. So you might see another issue with this program. When I don't enter anything into it, it just crashes. What's going over there? It's a logic error that we're not going to get into today, but you might want to explore afterwards on your own. So now we get our segmentation fault crash. Okay, so we have a value for ESP that looks like it's at the very top of the stack. That other value we had before was a randomized value with ASLR, putting the stack at an unpredictable location for the start each time. So we could just jump to this address and put our shellcode right there at ESP, and we should be able to execute our shellcode. So let's make our function to exploit the 1.py. So we're going to do the same thing that we had before with the 152A's. Let's make a variable for it this time. We'll pad with A times 152. Our payload is going to be the padding plus the value of ESP. So that will be B0, F0. FFBF. And please call me out if I typed that incorrectly. And then we're going to add our shellcode in here. This is just basic shellcode that I got from ExploitDB. Whenever you get shellcode off the internet, try to understand what it does first before you actually run it in production on your own system. Or else you can end up with some very interesting shellcode, it turns out. So let's go to our README file. This is our escape shellcode. And we're just going to want to print this out and make sure we're using R so that it prints in escape format. If you look at exercise E1.py, I included a way that we can not have to do this escaping and type it in the forward format. Should it be 0B? Let's take a look. No, it should be B0. So bytes are immutable. They do not change the order. What does change the order is the bytes within whatever memory unit we're using to access it. So B0 is going to be in the same order, F0 is going to be in the same order, then FF, then BF. If I am correct. And let's copy and put this into our program now. See if we can actually get this to execute as well, not using the shell function that was already compiled into the program. So let's run wisdom e1.out. And continue. Enter some wisdom here. Process is executing a new program. It worked on the first try. So as I talked about with ASLR, it's not always going to be pointing to that exact location in memory. Let's take off the no ASLR training wheels now and enable ASLR with echo 1 to process kernel randomize underscore VA underscore space. That is in your file as well. And we're going to want to find some way that we can get to the stack pointer regardless of what memory address it's located at. So x86 instructions have a variable length, and that means that not all instructions are the same length. Other assembly architectures, such as MIPS, use 4 bytes for each instruction. However, x86 is big on efficiency of instruction length, so they're trying to cram as much into it as possible. If one instruction turns out to be more popular than the others, then that instruction will be shorter. For example, only 1 byte when you're using increment ECX, whereas for a longer instruction that reads memory might be 6 bytes. So we're going to use what's known as a trampoline in order to jump directly to the stack pointer. Even though there might not be a jump ESP instruction that's legitimately in the program, why should there be? Why would we want to execute code off the stack? You've got to keep them separated. We might be able to find it compiled like in the middle of another instruction. GDB provides a functionality that we can do exactly for this. With the PD extension, we can use the jump call on our program, and it will tell us all the places that we might want to get to jump to a specific register. So let's go ahead and compile our part 2. So this is the one that has the different file for it. And it's a bit simpler of a program. Looks like it didn't get cloned properly. And change into overflow again. So we'll do GCC over in here in our subdirectory. Okay, it looks like the function the program compiled properly. We got our wisdom e2.out. So let's go ahead and run that. Escaped. Now we've only got the options that only matter in this case, with the receive wisdom or add wisdom. Let's hook to it with GDB. And use jump call. So we see this one instruction here, jump ESP, where if we execute this, then our flow of control will go to the stack pointer. That's where EIP will be pointing next, and that stuff will get executed. So if we were to replace the address of the actual ESP with this gadget that will get EIP to be ESP, it has the same overall end effect of what we want to do. So let's go ahead and add wisdom. And we're going to modify our exploit from exploit1.py. And we're going to put in the same reverse address here. Not the same address, but also in reversed format. So that would be B3, not V, 8D, 0408. And let's see if this does what we want it to do. That shellcode will still be valid because we're on the same platform. Let's generate exploit2.py. This generates the escaped input, but we're escaping the input before we send it into the program, so that's good. We enter some wisdom here. The process is executing new program bin dash. Are we in again? Yep. Oh, I'm typing in G to B, so that's why nothing's happening. So now we see we do indeed have a shell. All right, so now we're going to bypass this annoying NX bit. We're first going to do it without ASLR and then do it with ASLR, or at least that's the original plan, but I'm just going to jump through straight doing it with ASLR one. Let's do hardcore. But normally you would want to test out each new mitigation technique that you're doing first before jumping straight into doing it all at once. So here's a quiz for you, and just shout out the answer. If you want to answer no to this question, how would you answer no? Yes, exactly. We can circle that NO. This is what happens when you have an executable stack, like what I was talking about, when they're not separated and the EIP can point to the actual stack. So, we're going to use a function that's already in the program instead of jumping to the stack to execute our shellcode. This is going to be called a return to libc type of attack. So what we're going to overwrite with when we get into our function is a fake stack frame. We're going to put the address of system as what we want to return to. Then whatever we want to return to after that, which is not important here. And as the argument to the function, the address of the string that we want to call with system. So system is compiled in this program. It's not obvious like the shell function is. You won't see it in this program's source code, but by importing the standard libraries, we do have access to this function. And this problem was what happened with the Apache struts vulnerability. Very few people were actually using the deserialization feature that it provided, but since it was in the program, it affected all of the servers that were running that version of Apache struts. So let's go ahead and write our exploit here. So ASLR is on now. So system and bin sh may not always line up at the same point exactly. Well, how does the program itself deal with this? I mean, you can't call a function if you don't know its memory location. So what it has is called a procedural linkage table, or PLT, that contains a jump or a trampoline to the actual function itself. And you can call this function just as well as any other function, and that's what the actual function is going to be calling in the binary. So could we just call this function ourselves? Yes. That's so dumb it makes me mad. We can just call this function with this PLT stuff that's compiled into the binary, completely defeating the purpose of ASLR. So let's try it on this binary. We want to see all the functions named system. Let's do our compilation for exercise 3. Less on readme.md. And we're not going to compile without NX, so we are compiling with NX. And we're going to run our wisdom e3.out in escaped format. And let's make sure there's no other instances of wisdom currently running. There is, so we're going to quit out of that. Killing it ruthlessly. And now let's see the address of system in our binary. And looks like that was the correct one that I killed, actually. Why did I do that? And so we see we might have some functions masking system in here. And if ASLR is on completely, then we would also have a procedural linkage table in here. And we could call that function directly. It looks like we're down to 1 minute left, though, so I want to make sure I get any questions before we finish up from the audience. Okay, so we are just going to use the address of system here, and we will be able to do the same thing. So we didn't make it through to stack canaries. I didn't expect to. This is a rather ambitious thing to do, but we did see how to exploit ASLR and NX and make use of functionality in a program that you may not know is there. So this is not it. You can explore further on your own by doing challenges such as war games. The CTF at DerbyCon itself does have some reverse engineering and binary exploitation challenges. And also, if you want to go even further, you can find out what other people have been finding new exploits for by going on ExploitDB. It's almost a never-ending CTF, as people post continual exploits for new software